Okay, hi everybody. Um, I, I want to do a little bit of a review and maybe fill in the cracks between stuff. I feel like this remote learning is, things have come out in little bits and pieces. And I haven't actually had an opportunity to kind of run through like the key vocabulary and key ideas that we've been going over in class. Um, and then maybe a couple of things to set the stage for our next unit, right? So we basically have done the first 5 chapters in the book, and we're moving on into chapter 6 this week with chemical reactions. So let me kind of summarize the chemistry stuff that we've done, not like the mathy background stuff, but here's what we started is we started talking about the difference between physical and chemical changes. That is, the universe is made out of compounds and elements, and as it changes, there's two distinctions we want to make about these changes. One is the physical changes that can happen, like changing the states of matter from solid to liquid to gas, which doesn't actually change the composition of the individual units, right? What we now would call compounds, molecules, elements, right, that are bound together in a certain formation. Those individual subunits are the same if you do physical changes, right? Tear a sheet of paper in half, it's different sizes, it's got different edges and all that kind of stuff, but the molecules inside of there are still the same. Same thing if you boil water into steam, it's still H2O either way. On the other hand, a chemical reaction, you're actually going in there and breaking some bonds between the atoms and then rearranging them. The atoms are still the same, but they get rearranged into new compounds, and they have totally new chemical properties, right? They can be different colors, different smells, those kind of things. Compounds versus elements. So compounds are elements, are atoms that are bonded together in a certain way that create the molecules that make up everything in our life. The elements are actually the smallest subunit of matter that has that same identity, right? Those are the squares in the periodic table, right? The hydrogens, the heliums, the carbons, and all those kind of things. So those are the unique smallest constituents of matter that participate in chemical reactions. Pure substance versus mixture. So if you have a pure substance, that means everything in that sample is made out of the same molecule or the same element, right? It's every subunit in there is identical. Like if you have a vat of pure water, everything in there is H2O. That's a pure substance. Most water that you encounter in your life is some kind of mixture where there's stuff mixed in with the H2O. Like your tap water has fluoride in it and, trace metal compounds and things. It's tested so the stuff in there is only safe, but it's definitely not just H2O. And that's, of course, why water can taste different from different sources. Mixtures can be either homogeneous or heterogeneous. So homogeneous means that every time you grab a sample of it, you get basically the same mix, right? So like the air in this room, if I grab it over here, I'll get the same percent nitrogen, same percent oxygen than if I grab a sample over here. Things that are visibly differentiated that you can make out with your eye, those are definitely heterogeneous, right? You grab, gravel from a gravel pit, you're not going to necessarily get the same size rocks in there from a different location or something like that. So here's an important distinction, right? If you want to break a compound apart into its individual atoms, that requires a chemical process, right? Because they are bonded together, right? And so you need an actual chemical process to break some bonds to break them apart. If, on the other hand, you have a mixture and you want to separate it into its pure substances, right? Like you want to separate the H2O molecules in your tap water from the additives and the residual stuff that's in there, you can do that by filtering and other physical processes, right? So you can break mixtures into the various pure substances that they're made out of by filtering and centrifuging, doing a lot of physical processes, but the compounds need a chemical reaction. All right, then we started talking about, what is an atom? What is it made out of? And we talked about the history of that. So now we know there are basically 3 important subatomic particles that make up the atom, and they have very different roles, right? So the atom is on the outside, and most of the volume is occupied by electron orbitals, right? It's mostly empty space, but the electrons are hanging out in there, and those are the negatively charged objects. And they have hardly any mass at all. They do have some mass, but it's very small. And they provide the negative charge in there. And it is the exchange of electrons and that drives all of chemistry, right? And it is also the reason why atoms will become charged and be known as ions, right? If they gain, most atoms are neutral. That means they have the same number of negative charges as positive. The positive charge is in the nucleus. The nucleus contains most of the mass. That's where the protons and the neutrons hang out. It's a very small fraction of the atom. It's tiny, orders and orders of magnitude smaller than the whole atom, and that's where all the protons and neutrons hang out. So that's where all the positive charge is, and that's where most of the mass is. So an everyday atom has an equal number of protons and electrons, so that it's neutral, right? If it does become charged, we call it an ion, and it can become a cation, which is positively charged, by taking away electrons, right? Nobody's messing around with the nucleus in a chemistry class. That would be nuclear physics, right? You'd be having a nuclear reaction, like a bomb going off or something, a nuclear bomb going off. So the exchange of electrons are creating the ions, and it's the exchange of electrons that drives all the chemistry. Too few electrons, meaning you've lost some. Now your atom is positively charged, you're a cation. Too many electrons, so you've gained some from the environment. You now have more electrons and protons, so you're negatively charged ion, so you're an anion, right? And you designate the ions by putting however many, indicating what the net charge is, in a superscript to the right of the elemental symbol. Let's see, I skipped over this point down here. So the mass number, atoms on the periodic table, elements are identified with their number of protons, right? You can't say it's the number of electrons because you might have extras or fewer. You're still the same element. You're just an ion of that element. And it can't be the number of neutrons because you can also have more or fewer neutrons, in which case you're a different isotope of that same element, right? So the number of protons locks in the element. The number of neutron locks in the mass number, which identifies the isotope. So that's what carbon-12 versus carbon-14 is. Since it's carbon, it has to have 6 protons in there. Carbon-12 has 6 neutrons in addition to it. Carbon-14 has 8 neutrons in addition to it. So same element, you expect it to chemically interact the same because the number of electrons is driven by the number of protons. But carbon-14, of course, is a little bit heavier and has different nuclear properties, right? Okay, and then after that, we talked about how the ion charge drives how the compounds and molecules get together, right? And so we talked about how to write down a compound and how to name them, right? So some compounds are easily determined by the periodic table, in which case you just take the negative one, the anion, list its name first, take the cation, the positive one, and list it second and change the ending to IDE. If there's some ambiguity about how many of each that you'd have, these are the subscripts are telling you have 2 nitrogens and 5 oxygens, right? So by looking at nitrogen and oxygen, it's not quite so clear how many atoms of each would get together in the molecule. So anytime there's any ambiguity or variation, which tends to be when you have 2 elements from the right-hand side getting together, then you have a molecular compound, and then you're going to use these prefixes to nail down exactly how many, right? So nitrogen tells you have 2, pentoxide tells you have 5 oxygens. Right? You don't need the prefixes if it's like a non-metal and a metal, and everybody kind of knows what the charges are. Another way you can do it is if you have a transition metal, and I'm going to talk about periodic table here in a second. You can identify what type of, which of the many ions you can have. So the transition metals don't have a set number of electrons that they lose, right? It could be like iron can lose 1, 2, 3, or 4. And so you indicate by a Roman numeral afterwards so iron Roman numeral 2 means that it became a +2 cation. And then we introduced the idea of polyatomic ions. So there are certain groupings, they're not molecules because they're charged, right? So they're ions that travel together, right? In chemical reactions is what I mean. So when the bonds are broken, they tend to stay as a subunit, right? You can imagine a big complicated Lego piece, and if you break it apart, there are parts of the Lego piece that are more tightly snapped together, and then they'll stay together. Those will be like the polyatomic ions. They have their own names, which you don't have to memorize. They tend to end in ATEs and things like that. But there's a chart of them, and you should recognize when you see them, and then use the chart to actually, get the exact formula and stuff like that. And they basically replace. You just put them in parentheses and you replace a single element. So like if you needed 5 sulfates, you would put the formula for sulfate in parentheses and then put a little subscript after the parentheses to indicate how many of those ions you needed in that molecule. So I'm going to go over here. I've got the periodic table up, so I'm going to move the camera over there and talk you through a few things about the periodic table, some of which most is a reminder and some of it's new. But while I'm over here on this side of the board, let me just talk about where we're headed. Next is we're going to talk about how the chemical reactions are, what type of chemical reactions there are, how do you write them, right? The basic idea is you put all the molecular compound formulas on the left-hand side of an arrow. Those are the reactants. Those are the things that are going to react together and break each other's bonds, and then they're going to form new bonds. And you indicate that by an arrow, meaning that the reactants are going to the products, and then you put the new compounds formulas over here on the right-hand side. Now, sometimes you'll see a double arrow in the middle. It's pretty frequent to have a double arrow, and that just means the reaction can be driven both ways, right? So I wouldn't worry about that too much, but I just didn't want you to get confused. Sometimes you'll see a single arrow, and sometimes you'll see a double arrow. All right, over here I've got the periodic table from the inside of the book cover up on the overhead in the classroom. So, ooh, that is pretty faint, actually. Let's see what happens if I shut off the light. That's better. Not much better. Maybe I can turn the lamp on? Okay, I guess that's good enough. All right, so here's the periodic table. We already know the basics, but let me review it. Right, we've got the atomic symbols, which is 1 or 2 letters. First letter is always capital. If there's a second letter, it's always lowercase. You have to respect that. The element is defined by its atomic number. The atomic number is the number of protons, right? That's the single whole number, and that is how things are arranged in the periodic table, from 1 through the highest number down here on the bottom right. The columns, right, are called groups, and the rows can be called periods, right? So these groups or families of elements, why is it important to identify a column? Is because they have similar chemical properties, because they have a similar, they present on their outer layer a similar electron structure. And remember how I said it's the electrons that drive everything. So everybody in the second column, for instance, is hanging out with their outermost shell having only 2 electrons there. And so since the 2 electrons are kind of lonely on their outer shell, they tend to lose their electrons, and they tend to lose 2 electrons, and so they tend to become +2 ions. First column tends to become +1 ions. So they have names. The different groups have names. These are called the alkali metals in the first column, except for hydrogen, who's an outlier. Then you've got the alkaline earth metals that are in the second column. So, right, alkali metals tend to be +1. Alkaline earth metals tend to be +2. They were named before people actually understood anything about electron structure. Then these guys in the middle, these are the ones that we're mostly using the Roman numerals for. They don't have a set ionic charge. It varies a little bit in here, but in general, they're called the transition metals, right? And these are the metals that you don't normally expect to know just when I name the element. You don't say, oh, that one's always a +4 or whatever it is. And that's why they're structurally different on the periodic table. They're not as common either, right? The most common elements that you find are the first 20, right? After element number 20, the frequency of those elements drops quite a bit, with a couple of outliers, like there's a lot of iron on there. Then you get to the last columns. These also have names. The only ones you need to worry about are the last 2 columns over here. Right, so the very last column, these are called the noble gases, and the reason why is because they have a full complement of electrons on their outer shell, right? So they neither are looking to give nor receive electrons. So you rarely, if ever, see them involved in any chemical processes, right? And so they're noble gases. They tend to be gases at room temperature. And like I said, you will hardly ever see them in a chemical reaction because they're fat and happy, as I would say, right? Now, the column right next to them, they are the halogens, right? So that's a very common name that you should know for that family, for that column, for that group. And they are just 1 electron short of having a full shell. So they tend to grab an electron from their environment, and that would make them become -1 charged. The next column over, the oxygen group, is 2 electrons short, so they tend to be -2. Nitrogen tends to be -3, but as you get towards the middle here, you're somewhere, like you have 3, 4, or 5 electrons. Well, you could give electrons or you could take electrons, and it's a little bit less clear. But of course, the most common thing is for this row to become +3. The most common thing for the nitrogen group is to become a -3. Other things that you can tell from the periodic table, right, is that every time you drop down a row, what's making a new row and where does this periodicity come from is because you filled the electron shell and you're going out to another one. So every time you drop down a row, you tend to encounter much larger atoms, right? So all the atoms are slightly different size because they have different number of electrons. The nuclei are also differently sized, but that doesn't actually drive the size of the overall atom because the nucleus is so small, right? It only drives it indirectly because the number of protons gives you the number of electrons. So every time you drop down a row, you're stepping up in the average atomic diameter, right? The atoms are actually getting bigger and bigger. They're getting bigger and bigger all the time as you go down and down, but the row is where you actually are having a big increase. The other thing you have in the periodic table that is super useful is you have the atomic weight, right? The atomic weight is, we've done a couple exercises where we know how to determine that. You take the average of the naturally occurring atomic masses of all the isotopes, right? You take a weighted average, right? And so when you are grabbing a sample of calcium, right, any kind of handful or laboratory size sample of calcium has billions and billions of atoms in there. So it's going to contain almost all of the isotopes. And so it is highly probable that when you measure any kind of macroscopic, that is, quantity that you can see and hold and manipulate easily, a quantity of any of the elements, the mass that you will find for that whole sample will be the average mass, right? Because you have so many atoms in there. Metals, nonmetals, let's talk a little bit about that. So everything on the left-hand side, these guys tend to be metals, except for hydrogen. Hydrogen's an outlier. Everything in the first row is a little bit weird because it's so small. So you have kind of a dividing line along here, and metals are on this side. Metals are how you think of them, right? They tend to be solids at room temperature. They tend to be shiny. They're malleable, meaning you can bend and move it, and the ductile, you can make strands out of it. Over here, on the right-hand side, you have the nonmetals, so they are the opposite of all those. They tend not to be shiny. A lot of them are gases at room temperature. They're brittle, so if you try to manipulate and break them, they just turn into a powder or something like that. And then in the middle, in the area that's transitioning from nonmetals to metals, as you would expect, those atoms are kind of in the transition. They have properties of both, and they're called the metalloids down here. Okay. I think that's everything I wanted to say. Okay. Sorry, the camera angle was funny.